Welcome to Chapter 2. We're going to be discussing chemistry as it is for our textbook, covering the topics of chemistry. We're going to describe what an atom is, the structure, and how, based on the structure and what we know about the chemistry and how they bond, understanding the features of one of the most important aspects of life, water, and describe carbohydrates, their structure and function as we proceed through the chapter of chemistry. Lipids, structure and function, and proteins and nucleic acids. All of these, of course, are the building blocks of life and are very important for our understanding of the life processes. And I understand at least chemistry is perhaps one of the least favorite topics that students usually endeavor in, and I want to try to change that for you. And chemistry really makes life interesting, and understanding aspects of chemistry can improve the quality of your life, and I'll prove that to you as best I can. An element itself is a substance that cannot be broken down chemically into anything else, so it's a fundamental basic concept, I guess, as far as what the whole matter of the universe from that standpoint, everything is made of. So gold, carbon, copper, all of these things are elements, and they are chemically unique, and at the atomic level they have properties that don't change. Thank God for that. So an atom is a bit of matter that cannot be subdivided into anything else without losing its essential properties. So let's examine just the atomic structure. If we look at the hydrogen atom, which is the simplest one, we have a very simple core where a proton, that positive symbol there, makes up the nucleus. The hydrogen atom is so simple it doesn't need the glue to hold the proton and the electron together. That's what neutrons typically do. One electron that probability-wise, somewhere in this cloud would exist this one electron. And so a carbon atom is a little bit more complex. It's a basic unit of life. We are carbon units. We utilize carbon in our bodies and tissues, and it is the formation of many forms of life. In fact, if it contains carbon, it's most likely alive. But so we have 6 protons, so we have 6 of these positive charges, 6 neutrons, the glue that holds and makes the positive charges behave within the negative electrons that spin around, and probability wise anywhere around. May I point out before we go much further, there's a little rule in chemistry, and it's called the octet rule. But what that means is we can only have 2 electrons on the first orbit, and then the next orbit that we can place electrons, the maximum number in that outer orbit there is 8, and then we can have another orbit beyond that with 8. So the octet rule says that these atoms would really prefer to have all 8 positions in the outer what they call the orbit, or the valence number is having the full number or complement set of 8. Carbon likes to share, like many other atoms, and will share with, let's say, hydrogen, and share these electrons. So we can have 4 more sharings with this. We're going to talk more about it. I just wanted to point that out so you could be thinking about that as we move on. So the forces that are attract, of course, for the atomic structure and held together are predictable by the basic structure itself of the 6 protons, 6 neutrons. So if we look at the periodic table, we can look at atomic numbers and various aspects of the periodic table. But before we do that, let's look at each element and how it's typically arranged. We have the atomic number, which is the number of protons found in the atom's nucleus. The element symbol, which is the abbreviation of the element's name. Now, some of those might appear a little bit weird, like gold is AU, and that was Orium. A lot of those are based on some of the Greek or Latin terminology, and that's why some of the names have been changed to protect the innocent. The element name, the atomic mass, combined mass of the atoms, protons, and neutrons. And we usually use the atomic mass when we're calculating molarity, when we're trying to make chemicals that we can actually use in experiments. And this book likes to use color codes, and they're pretty consistent. So hydrogen, carbon, nitrogen, oxygen, sodium, phosphorus, sulfur, chlorine, potassium, calcium, pretty much all the ones that we're going to talk about. Maybe some of the trace elements, but those are the ones that we're going to try to limit our discussions here. So the elements that are found in your body, and the big four, we have oxygen, carbon, hydrogen, and nitrogen. Our bodies are composed of a hugely amount of water, and then all of the proteins and various other atoms that are arranged in such a way to make up our tissues are composed of the others. Now 4% calcium, phosphorus, potassium, sulfur, sodium, and chloride are essential as well, but they're just not present in the same high degree order as the others. So everything around us, living or not, is made up of atoms, the smallest unit in which material can be divided. Atoms all have the same general structure. They are made up of protons and neutrons in the nucleus, and the electrons, which circle around the nucleus. So the atom's electrons determine how and whether the atom will bond with others. And these are the electron shells, as I was making reference to before. If you look at the electron shell, the electrons move around the nucleus designated areas called electron shells. The atom can have as many as 7 electrons in shells total. We can have actually in the outer ones 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. In the oxygen, we have 1, 2, 3, 4, 5, 6 actually there, and then we have now vacancy for 2 more. So this labeling here is 7, should be 8 electrons in shells. Oh, okay, it says 7 electron shells. Yes, we can have 7 shells. I was thinking there for a moment that it was the electrons, so I don't want you to get confused on that. If I get tripped up on it, I'm sure that you might as well. So the total number of electrons in the outer shell has to be 8 due to the octet rule that we discussed, but we can have up as many as 7 electron shells. We're only going to really concern ourselves with up to 3 in this course. At atomic stability, atoms become stable when their outermost shell is filled to capacity. They like to have those filled. Ones that play well don't play well in elementary school is the neon atoms or the helium atoms. These are inert. They have everything filled. They don't need any interactions, and they're just fine on their own, where nitrogen and hydrogen, for an example, would like to have more, and that's a part of the chemistry itself. So we can have ions in order to achieve this full. So sodium has only 1 on its outer shell, and it will give that up. As soon as it loses an electron, it becomes an ion. The same follows if you have chlorine and you need an additional one that normally is not there. Obtaining that additional one makes it an ion as well. So the ionic form is an unusually charged atom, and then it makes it more interactive because it now actually has a charge. It's acquired it permanently and unless otherwise acted upon. So the chemical characteristics of an atom depends on the number of electrons in their outermost shells. Atoms are the most stable and least likely to bond with other atoms when their outermost electrons are full. Of course, there's no way that they can interact. Atoms can bond together to form molecules or compounds. Well, not only can they must in order to form various aspects of life. So Molecules are the products of bonding, which makes sense. So covalent bonds, think of covalent as sharing. Co meaning cohabitate or together. Valent, so we're sharing the valence of two atoms, and we form bonds, a covalent bond. So hydrogen itself, if you have hydrogen binding to itself and sharing two molecules, they will share one electron for each. That's thus satisfying at any one time, having two electrons in that inner valence so that they're satisfied. So H2 molecule is a very stable molecule. Other examples are O2. If you recall, we needed to have two more electrons, and oxygen can now share two together, so it would be an O with two lines, and another O is another way of representing this. Or carbon, as I mentioned before, the inner valence is full, but the outer needs 1, 2, 3, 4 more, and the hydrogens donate that additional hydrogen, and it needs an additional electron. And so sharing these two electrons between the hydrogen and the carbon in each of these cases builds a more stable atomic structure. So ions and ionic bonds, now we mentioned an ion is either they've lost or gained an additional electron from its normal state, and that becomes ionic. And a good example would be salt. When we form sodium and chloride, sodium now will be electrically attracted to the chlorine. So we have a sodium which is a positively charged because it lost an electron. If you remember, the proton number didn't change, but the electron did. In chlorine, the proton number didn't change, but the electron count did. So it has an additional electron, making chlorine a negative where sodium is positive, and as a result of that we get a lattice structure that we know as table salt. I hope that makes sense to you. As we proceed through, hydrogen bonds in water, hydrogen nucleus with the only single positively charged proton doesn't attract negatively charged electrons as much. So one way to look at this, the way these share, we have a little bit predominant negative, what I like to consider a bald head on the top of the oxygen, and the way the bond angles work and sharing of these electrons, the hydrogens associate sort of as at another end or a pole of the oxygen. So the net result is that we get more of a positive like charge down here, a partial charge, where at the top we have a sort of a negative partial charge with the oxygen. And so that refers to this bipolar nature of the water molecule. So all the electrons spend more time near the oxygen, thus making the side of the molecule slightly positive and the hydrogen side slightly negative. And this is a very unique characteristic of water, having this bipolar, this dual charge nature to it. And what this affords water to do is to have a hydrogen bond-like attraction. The negative region of that, with that bald spot of that oxygen, with the hydrogen portion of another water molecule, and this adds to that cohesive like force. That's the strength of that is van der Waals force, and that is equivalent if you've ever had a balloon filled with the helium gas, and you rub that balloon on your hair. There's a electrical static charge that's formed, and it tries to lift your hair if you've ever experienced that. That's equivalent to the electrostatic forces, or the charge that we see here with the hydrogen bond, with that amount of force that you can generate with that, and that's van der Waals like force. So covalent bonds are sharing. Whenever you see the word co, just think of cohabitate or sharing. Valent bond, H2 molecule is an example, and an ionic bond would be sodium chloride, and then the hydrogen bonding would be that weak attraction with the van der Waals like forces between water molecules. And this is why water, well, if you look at gutters, they'll tend to go around the outside of the gutter, and that's a cohesive force, and it will follow along because of that slight charge here. And so of strength, the strongest would be the covalent bonds, ionic bonds sort of in the middle, and then the weakest are these hydrogen bonds. Atoms can always be bound together in 3 different ways. Covalent bonds, in which atoms share electrons, are the strongest. Ionic bonds, the next strongest. The one atom transfers its electrons to another, and 2 oppositely charged ions are attracted to each other, forming a compound. So the ionic bonds do follow. We have a negative and positive charge, and that should become obvious to you. Hydrogen bonds, the weakest, involve the attraction between the hydrogen atom and another polar atom or molecule. So water is that dual purpose. It has a positive and negative like feature to it, so whatever it's attracted to, either positive or negative, the structure will just spin around to match that charge. That's why water kind of dissolves everything. It's a universal solvent. A molecule's shape gives its unique characteristics. Shape is so important with these structures. I always say structure and function. You'll probably get tired of me saying that, but I like the idea of this molecular personalities. It really does dictate the unique charge around various types of molecules, and the shape really decides how it interacts with more advanced type of interactions like enzymes or catalysts and that sort of thing. Shapes determines the function, the physical properties such as taste and smell, all sorts of things. So the chocolate has a glucose molecule, and we have certain receptors on our tongue that look for particular shapes or structures, and you can see that the salt and sweet, and we have bitter, various other ones that shape. It's sort of like a key and a lock. Each has its own unique shape. Molecular interactions in insect mating behavior. We have pheromones. Pheromones are unique from the standpoint they have an attraction for these types of pheromones for each type of animal, and in this case the male gypsy moth can detect and track a female as far as 2 miles away if it's encounters a molecule. Sort of, you think of a sexual pheromone as a cologne of some kind, but it's a molecular cologne that has a unique shape, protein that the other gypsy moth can detect. It's a very unique structure for it. The properties of a molecule, such as how the molecule tastes or smells, its likelihood of bonding with another molecule, depending on the shape at which the atoms are linked together, and the electrons in their outermost shell. So we're building now. We build these molecules, and then the overall molecule resulting structure will have a unique function as a result. Okay, so that should be pretty straightforward. Water has features that enable to support all life. I told you it was the universal solvent. Water has a high surface tension. So here's a little insect that can literally float on the surface, and because of the hydrogen attraction between the water molecules, this particular insect has hydrophobic, or regions that do not like water, and because it's stretched out over a long surface area, that's why the insect doesn't sink. It can actually now literally float on top of the water without getting wet, and just utilizing the surface tension created by the water molecules itself. And same as that's me enjoying summer when I'm running across the water. But the surface tension of the water does make some very interesting characteristics. So pressure applied to the surface, if you know the interactions that we've just talked about with the hydrogen bonding, that if you don't exert enough force to actually break that weak attraction, you can actually stay on top. So like that insect can, and it's just enough strength to give it that integrity, and that's surface tension. So the the water glider there has that feature to be able to do that. So that's a good thing. Water molecules easily form hydrogen bonds, giving water its great cohesiveness. So the surface tension is due to this cohesiveness. It's sort of like adhesives of glue. Cohesive is the chemical attraction for each of the water molecules. So water has unique properties: the cohesion, large heat capacity. So if you remember, if you go to the ocean, you can feel a cooler temperature, and that is a reflection of this heat capacity that we're referring to. Low density as a solid. It actually floats, as you know, ice cubes will float, and it's a good solvent. It is a universal solvent. Cohesion, of course, we have the xylem and phloem in these special structures within plants in order to move water, to give it its tuger, its water pressure, to keep the plant fully vascularized there with water. So you can see the water cohesiveness actually helps pull the wicket up. If you've ever used a siphon is sort of a siphon effect. If you start the flow, if you notice with a siphon, it will continue to flow, and that's due to this cohesive effect of water. Other molecules or substances like gasoline will have some cohesive like force if you can get the siphon effect going, but the xylem and phloem in a plant uses this sort of this flow effect that I was just referring to. So heat capacity, heat energy from the sun disrupts some of the hydrogen bonds between the water, and what that does is dissipate some of the heat. So that's why the air will feel somewhat cooler. New hydrogen bonds are formed almost as quickly as they're disrupting. So because heat energy from the sun is used up for breaking and reforming hydrogen bonds, the water temperature doesn't increase much. Molecules that make up the sand and on the other hand, don't have these hydrogen bonds, so the heat of the sun increases. So that's why the sun will heat up the sand and ouch, ooch, each as you walk across, but the water is nice and cool. So 60% of your body is water. It helps you maintain relatively constant body temperature. It's one of the characteristics of this heat capacity. So why do the coastal areas have milder, less variable climates than inland areas? Well, that's obvious. That's because of this capacity for the sun to hit the water, and the energy for that is actually used. Energy is not created nor destroyed, it just changes form. So the bonds are broken but immediately are reformed, and so that keeps a nice thermal stability in that coastal area. And frozen water forming a lattice structure with more spacing. As a result of that spacing, it's less dense and the ice will actually float, versus in liquid water you have a randomness, and you can pack water molecules a little bit more tightly when it's liquid. So frozen water actually takes up more space than liquid water, and hence the floating of the ice cubes. Water's a good solvent. It's a great solvent. And when placed in water, ionic compounds like sodium chloride are broken down because the inherent bipolar nature of the water molecules will neutralize the charges, and then the sodium chloride will disassociate, and then which is a good thing, because I like to have salt on my foods there, and that's a good way of doing that, of dispersing it. Why don't oceans freeze as easily as fresh water? Why do you think that is? Well, that will reduce having salt molecules will reduce the water's ability to freeze, primarily because it takes energy now to break the chemical bonds and then form that lattice structure. So it will take more energy, and so hence it take more of coldness in order to make ice form. Hydrogen bonds between water molecules give water several of its most important characteristics. Again, are cohesiveness, low density as a solid, ability to resist temperature changes, and broad effectiveness as a solvent. Living systems are highly sensitive to acidic and basic conditions. And so we have ionized hydroxyl molecule. This is an OH, and a non-ionized water molecule is H2O. When you say ionized, what happens is that we lose an ion, and like hydrogen, in this case we have OH and H2O. So this will actually have a negative charge because it wants to seek and fill that additional electron in its outer valence, where H2O has a bipolar-like feature because it is a water molecule with this bald spot up here. And then of course the proton, or hydrogen, is what's not mentioned here, but it can be a free species as well. So pH actually means percent hydrogen, pH, and that's the amount of protons or hydrogen in a solution, is a measure of its acidity, and it's called pH. So that's what I would want you to focus on. 100% concentration of protons with 0 hydroxyl groups is an acid. And the corollary to that is if you have 0% hydrogen and 100% hydroxyl, or that OH group, then it's a base. And if you can remember that in pH, you'll be doing yourself a great favor. So if you look at the pH scale, we go from 0 to 14, and there's a reason for that. Of course, it's man-made, or human concept. But 0 is 100% proton, or H plus, and 0 hydroxyl. Where at the other end, at 14, we have 100% hydroxyl and 0 proton. So that is the whole range. So they're inversely proportional, which means if I have something with, let's say, 20% hydroxyl group, then I have 80% of the proton, and that follows. Right in the middle, we have 50-50. We have 50% concentration of hydroxyl and 50% of the proton. That's pH of 7. So acids are fluids that have greater proportion of the protons or hydrogen to the hydroxyl ions. And bases are fluids that have greater proportion of hydroxyl ions to the protons or the hydrogen ions. So you can see that that really is all that pH is talking about. So we're going to talk more about that as we get into the lab and other times in class. So protons are very reactive. Acids can donate the protons to other chemicals, and we use that to break down things in our stomach. Of course, we have the stomach acids around 1.6 or so, and that does most of the work. Bases have low protons but a high amount of hydroxyl. Antacids, baking soda, seltzer, milk of magnesia, and that sort of thing have a lot of hydroxyl groups, and we form water once it interacts with hydrogen. So buffers resist changes in pH. That's what a buffer does, and that's what a buffer is. In the blood pH, we have to maintain a pH of 7.4. If we vary to, let's say, 7.58 or so, or something like that, that's not compatible with life. We have to have a very strict control of pH. So in our blood, of course, we would have to buffer blood quite well. So buffers can quickly absorb excess hydrogens, or the proton ions, to keep a solution from becoming too acidic, as they quickly release proton ions to counteract any increase in the hydroxyl concentration. So what's happening is the buffers are trying to resist the changes in pH by monitoring the concentration of the hydroxyls or the protons, depending on which side of the equation that we're talking about. So the pH of a fluid is a measure of how acidic or basic a solution is, depending on the concentration of the dissolved protons. So that's an easy measure for equipment or chemically looking at charge. And the higher amount of protons that we have, then the lower the pH. Acids such as vinegar can donate protons to other chemicals, while bases, including baking soda, bind with free protons. So they take protons out of the solution, and hence making it more basic. I hope you follow that. You can ask questions about that in class if you have any concerns about that. Carbohydrates for fuel for living. Carbs is synonymous with getting energy. Carbohydrates are macromolecules that function as fuel. Low carb diets, high carb diets, carb loading, fiber intake, all are these things. A carbo or carb are strings of carbons with a certain amount of OH and H groups, depending on what kind of molecule it is. And so that's where the word carbohydrate comes from. So we have 4 types: carbohydrates, lipids, proteins, and nucleic acids are very important types of macromolecules. Macro just meaning large, so large molecules. We'll go from there. So carbohydrates contain carbon, hydrogen, and oxygen, primarily fuel for organisms in its cell structure. So we break energy bonds within the carbon, and that is the energy we use for so the overall contributes greatly to the cell structure. Of course, the glucose, when we break these bonds, the physical breaking of the bond itself provides this form of energy that we need to charge our universal currency in our bodies called ATP. And ATP has a unique chemical structure that when we release that energy will help either change the shape of proteins, we're going to talk about, in order to do functions like enzymatic activities and various things where we actually move or change shapes. And that's part of the energy that these molecules do to an overall a cell, or the function within a cell. We'll talk more about that. Don't worry about it right now. So energy is the chemical bond, and chemical bonds are a good way of storing energy and then actually obtaining energy from them is when we break them. So carbohydrates are the primary fuel for running all cellular machinery and also form much of the structures and cells of life forms. Carbohydrates contain carbon, hydrogen, and oxygen, and generally have the same number of carbon atoms as they do H2O units, so you can look at it that way. CH bonds of carbohydrates store a great deal of energy and easily broken down by organisms, and they break down in a similar way, so it's universal. Of course, all that energy comes from the sun, but we'll talk more about that later. Simple sugars are the most effective source of energy. Mono meaning one, saccharide meaning sugar. Saccharide is Greek for sweet tasting or sweetness, so saccharide is referring to a sugar. Mono is 1. 3 to 7 carbon atoms. Glucose and fructose are good examples of monosaccharides, very common forms of sugars. So we have glucose, and we see in 3 different ways we can represent a glucose molecule. We have the typical 1, 2, 3, 4, 5, 6-sided structure, which can be represented in this 6-sided structure. So glucose, we have this 1, 2, 3, 4, 5, 6 of the bonds. So 1, 2, 3, 4, 5, 6, and then we have the upper chain. We can talk about that later, but we also can refer to it as C6H12O6. So you might see any of these representations being used at any one time. Fructose having the same structure, C6H12O6, yet it does look 1, 2, 3, 4, 5 sides. What happened here? Well, we put an additional side chain on it, so we obtain still the 6 carbon structure. And then the glucose has C6H12O6, but its changes are on the position of which way the hydrogens go, and I can show you this in class with a slightly different diagram to help illustrate that. But if you notice, between glucose, this hydrogen is pointing this way, and this glucose is pointing a little bit higher. I know that's a subtle point, but that's the only difference between galactose and glucose. So representing it in either this form with the C6H12O6 doesn't really do it justice. It does have an impact when we actually look at the molecular structure. So that's why we use different representations. This diagram and this diagram look the same other than its color, so it's not that useful in delineating its features. Glucose, most carbohydrate ultimately converted, that we use blood sugars. We hear a whole lot about this now when we talk about diabetes and energy. So energy is needed. Molecular bonds are broken down by your cells. Energy that's not needed, we store it, and if short term is glycogen, long term is fat within our systems. So what is carbo-loading? And that's getting a good amount of carbohydrates and eating them right before you burn them. So before we store them to fat, we actually utilize them so we can have more energy and feel like we can ride or exercise for a longer period of time. And a lot of athletes will do that, and they'll load up with carbohydrates and exercise and burn, and not so much store them. Why do dieters lose a large amount of water during the first few days of a diet? Well, in the process of breaking down these stored sugars, every ounce of stored glycogen has as much as 4 ounces of water bound to it. So we actually take water out when we break down these bonds, and water weight loss actually is excreted pretty freely during urination, of course. And so to the demise, not the demise, but to the displeasure of a lot of dieters, that they thought that they've lost fat, they actually have lost a lot of water. So breaking down fats is all part of the process of breaking it down. So the simplest carbohydrate are called monosaccharides, or simple sugars. They contain from 3 to 7 carbon molecules, and the sugar glucose is the most important carbohydrate to living organisms, which makes sense. Complex carbohydrates are time-release packets of energy. More than one sugar or monosaccharide unit, mono, one, saccharide, sugar. Disaccharides have 2 sugars, sucrose, lactose, are linked together, and then polysaccharides are more, usually 2 or 3 or more. Starch or cellulose, a repeating structure, big long chains, are very typical. Of course, that makes up starch, and cellulose is repeating structures. So chemical fuels, as you can see, is the complex carbohydrates, and we can form bonds between the simple sugars and make chains, the disaccharides and polysaccharides, and then break these down during digestion in order to harvest the energy back. And that's really the basis in the formation of life, and life processes are based on that. So starch, over hundreds of glucose molecules join together at any one time. Barley, wheat, rye, corn, rice are all forms of starch, and glycogen are forms of animal starch. So we have those formations of starch itself. Complex carbohydrates are another way of looking at it is time-release fuel pellets. And depending on their structure, dietary carbohydrates can lead to quick but brief, or slow but persistent increases in blood sugar. So fructose for complex carbohydrates, depending on time. So immediate release is fructose. So if you wanted some immediate energy boost to support maybe weightlifting or jogging or something, fruit would be a good source. Or a complex carbohydrate takes more time to break it down, and you get a more even distribution or release over time. And these are dietary considerations that one should have in trying to form a good diet for yourself. Multiple simple carbohydrates sometimes link together into more complex carbohydrates. Types of complex carbohydrates include starch, the primary form of energy storage in plants, glycogen, the primary form of energy storage in animals, both of which we somehow consume in our diets. Not all carbohydrates are digestible. Chitin and cellulose are two examples. Now these have to be broken down, at least in the cellulose point of view, by bacteria. The only difference really on how these are linked together is sort of like linking upside down. So enzymes or normal processes have trouble breaking these bonds. And for an example, a cow or a ruminant would chew its cud, as you know, and eating grass, and then in the stomach compartments of this cow will have lots of bacteria coating the food, and they break down the cellulose into the carbohydrates or the glucose molecules. And so the plants have worked hard to try to encode or to keep that glucose from being stolen, but the cows and bacteria friends there have worked out a way for us now to eat that form of sunshine energy in the form of these broken down glucose molecules that are tightly and concealed in cellulose. And this is the same is true for termites. The termites will have a certain type of bacteria in the gut where they provide the breakdown of the cellulose as they're chewing your house as an energy source. And so chitin provides that hard shell with the lobster and that protection, or the cellulose that's located, of course, in the trees, which termites can utilize with bacteria friends in their guts. Now we do need indigestible type of materials. Fiber still aids in digestion, has numerous health benefits. A lot of times it's just clearing out our digestive tract of bacteria and the like, keeping a movement and causing fresh regrowth. We have 2 to 3 pounds of bacteria in our gut at any one time, so we need to have good fiber to keep things moving through and also keeping a good form of health. So fiber provides that roughage, colon cancer prevention and reduction by moving out bacteria. Now bacteria you think are harmless, but a lot of times certain types of bacteria can produce toxic chemicals and waste products that our cells don't seem to like very much, and will form different types of cancers as a result. Termites utilize trees in your house as a source of fiber, but really not as the same way because of the bacteria using that to break them down into the form of energy, glucose, and so they provide that service. And then of course the termites provide the bacteria a nice little moving home that is taken care of. So there's a symbiotic relationship there. So in summary, some complex carbohydrates, including chitin and cellulose, cannot be digested. Some indigestible carbohydrates in the diet, called fiber, aid in the digestion and have numerous health benefits. Lipids store energy for a rainy day. Lipids are macromolecules with several functions, including energy storage. So why does a salad dressing made with vinegar and oil separate into 2 layers shortly after you've shaken it? Well, like dissolves like, and dissimilar molecules will dissociate. So this concept of hydrophobic or water fearing, or hydrophilic or water liking, are 2 concepts and two terms that I want you to be familiar with. So lipids are nonpolar molecules that do not dissolve in water. They're greasy to touch, and they have a significant source of energy. Long-term energy storage, fats. Sterols are their function to regulate growth and development, sort of like on and off switch factors that turn these things on or off. Phospholipids are membranes, phospholipid bilayers, very important. So the green portions are hydrophobic regions that associate with each other, as you can see in the green part there. So like dissolves like, and then the phospholipids are the water liking, the portion of that they like, hydrophilic, so they'll associate with this in forming a membrane. And yeah, that was me in my last vacation. A lot of fat there, but it insulates and source of energy. Typical features of lipids: nonpolar molecules that do not dissolve in water, greasy to the touch, and significant source of energy. Lipids are non-soluble in water and greasy. They are valuable to organisms in long-term storage and insulation, membrane formation, as hormones, which are things that control on a grand scale. Fats are tasty molecules, too plentiful in our diets, of course. Glycerol head region, and you can see that diagram here. Fatty acids are these long chains. These are typically hydrophobic regions, and these are hydrophilic up here, and make up triglycerides. Triglycerides use 1, 2, 3 chains of these tails or fatty acids, so that's why they're listed. Fat molecules contain much more stored energy than carbohydrate molecules. Because fats store such large amounts of energy, animals have evolved a strong taste preference for fats over other energy sources, which it's a good source of energy, and our bodies will get used to that. So the number of bonds in the carbohydrate chain in a fatty acid. So if you look at saturated and unsaturated, we have either long chains in saturated fats or these little kinks because of double bonds. If you recall, carbon can share 2 electrons at a time, so we can have these double bonds. So unsaturated fats will have these kinks in them. So crooked fatty acids cannot be packed together tightly. As a result, unsaturated fats are liquid at room temperature, where if they're tight and stackable, they're solid at room temperature like butter. So there's your saturated. In other words, all the hydrogens that can possibly be added resolve in the covalent bonds are saturated. Unsaturated means that we could put more hydrogens to fill one of those bonds there, but in this case it's been double bonded, so we get this kink-like structure as a result. Chocolate chip cookies recipes call for some lipids. So chocolate chip cookie recipes are sugars and fats, so that's not a really good. How will the chewiness of the cookie differ depending on whether you use butter or vegetable oil? Well, at room temperature it'll be softer if it's a unsaturated particular fat. If it's saturated, it'll be stiffer at room temperature. Which cookie is healthier? What do you think? Well, the unsaturated fats have these kinkies associated with them and tend to be a little bit more healthy because they tend to move around more, but there's some debate about that, and we'll come back and talk about that and when we talk about nutrition. Many snack foods contain partially hydrogenated vegetable oils. Why might this be desirable to add hydrogen atoms to a vegetable oil? Well, if you add hydrogen atoms, then you tend to make it more saturated, so then they become saturated oils. Vegetable oils, of course, are liquid at room temperature because they are unsaturated. So the partially hydrogenated provides more of a manufacturing benefit than a health one. Trans fats are fats that have these kinks that will not do well as far as sticking to clutter in our vessels and causing now these atherosclerosis conditions in our heart. We'll talk more about trans fats. Hydrogenation is an artificial addition of hydrogen atoms to an unsaturated fat. This can improve a food's taste, texture, and shelf life. So it helps sales. So we have unsaturated fat in the cis form and partially hydrogenated trans fatty acids, or trans form. Hydrogenated trans fat increase your risk of heart disease. because they don't typically sit down as smooth, and there's all sorts of reasons. I don't want to oversimplify, and as I say, we'll cover more of this later on. Olestra is a recently developed fake fat chemical that gives foods the taste of fat without adding to the calories of fat. What chemical structure might make this possible? Well, one of the things is that we don't want to break it down in order to use it as energy. We want to have the enjoyable fat-like taste, but without the calorie hit. So it's the way we chemically bind these things. Unfortunately, the bacteria will have a heyday because they can break them down, like I mentioned in a ruminant. And as a result, you'll have that unpleasant and social faux pas of gas. So whichever you want to live with. Fats, including triglycerides, common in the food we eat, are one type of lipid, which is true. Characterized by long hydrocarbon tails, fats effectively store energy in bonds connecting the molecules. Organisms prefer fats in their diets because of the high calories, but this also causes obesity and illness in today's modern world. Just look around. Exercise plays a big component to that, as well as other habits. Not all lipids are fats. The steroids. So let's look at steroids, or sterols in this case. And cholesterol, important component of cell membranes in animals, can attach to vessel walls, causing them to thicken, which may lead to high blood pressure, stroke, and heart attack. And I always look at it as these might be equivalent to like panes of glass, and making the membranes that incorporate these a little bit more fragile. And so that's one way of trying to look at it in terms of why it's bad for high blood pressure and that sort of thing. Steroid hormones regulate sexual development, maturation. Estrogen influences memory. Testosterone stimulates muscle growth. So you can see estrogen and testosterone being very similar, just with losing a double bond here and a few other side attaches, but quite similar in lots of ways. These subtle differences make a profound difference in outcomes in living humans. Cholesterol, important component of most cell membranes, can attach to blood vessel walls and cause them to thicken. Cells in our liver produce almost 90% of the circulating cholesterol. So estrogen and testosterone, of course, you can see Arnold, he worked out big time to create all those muscles, but hopefully he didn't take any supplements, to generate those types of muscles. And you build up muscles over time, it turns to fat rather quickly. So it's one of the downsides of having so much musculature. Phospholipids are the major component of cell membranes. Waxes are strongly hydrophobic, and you can see that when you try to it's like you put a candle out. It's with water. So phospholipids is this unique hydrophilic head attracted to the water, and then you have the hydrophobic tails that are not attracted or repel. And like dissolves like, so these lipids will self-associate with themselves, and then the hydrophilic heads will associate with a water interface. And it makes life quite interesting. So cholesterol and phospholipids are lipids that are not fats. Both are important components in cell membranes. Cholesterol also serves as a precursor to steroid hormones, important regulators of growth and development. Proteins are bodybuilding molecules, and proteins are really important. They're versatile macromolecules that serve as building blocks: structural, protective, regulatory, contractile, and transport. And these are important to remember and aspects, and we're going to talk about the different things. The structural, which hair, fingernails, feathers, horns, that sort of thing. Protective, help fight against invading microorganisms or with our skin. Regulatory, control cell activity, constitute of course some hormones. Contractile, allow muscles to contract, hearts to pump, sperm to swim. And transport, carry molecules such as oxygen around your body or move certain products across membranes, and we'll talk more about those. There's 20 different amino acids strung together to make proteins. So they're like making beads, or you can think of it as railroad cars hung together in very similar ways. Of course, it's a repetitive type amino and an acid group linked together with a chain attached to a carbon and an R group that determines the 20 different amino acids, which we'll talk about. So here's the structure. Here's the amino group and the carboxyl group, and these are sort of the front and back of the connections that we have that we link the amino acids together. There's the carbon with the side chain, or the R group, and we can have one hydrogen that gives us glycine, or a carbon with a CH3 group, that's alanine, or we can have more complex things like tryptophan that has this cyclic aromatic ring structure associated to this. So and then you can look at the symbol for the amino acid that they use throughout the book, and hence I try to use slides that are consistent with the book, and I used the book company slides just to keep things consistent, easy for us to follow. Unique combination of the 20 amino acids gives rise to the proteins, which are the chief building blocks of physical structures, which is of course under genetic control, and we're going to talk about genetics here in a little bit. Proteins perform a myriad or a varied group of functions. Proteins are an essential dietary component for growth, repair, and replacement. And proteins, of course, are essential. And in fact, some of the amino acids that make up the proteins we have to acquire in our diet. We cannot manufacture those, and we'll talk more about those later. So food labels indicate an item's protein content. So why is this insufficient for you to determine whether you are that you're protein deficient, even if your protein intake exceeds your recommended daily amount? It's all about which of the proteins that we need to acquire, as I say, for essential amino acids versus ones that our bodies can synthesize. So we have to make sure that our diets contain the various ones that we must acquire from our environment. Complete proteins all have essential amino acids, incomplete proteins, and complementary proteins. So the complementary proteins and the like are all dietary types of concepts. Traditional dishes in many cultures combine proteins, bringing together all the essential amino acids, making sure that we include those in our diets. 8 of the 20 amino acids are essential, and I have a little ditty for that. A private PVT, TIM, TIM, HALL, Hall, private Tim Hall, are the first letters of each of the 8 of those amino acids that we have to acquire in our diet. So PVT, for an example, proline, valine, and threonine are examples of amino acids, 3 of them, and there's the rest. I won't have you remember that, but at least 8, if you can remember, we have to acquire in our diet. So complete proteins contain all 8 essential amino acids, while incomplete proteins do not, and hence the name as it's inferred. So peptide bonds, we have as a result of these peptide bonds and start linking them together like sidecars, that we have the primary structure, which is the amino acid sequence. The secondary structure is that the proteins will naturally start to form either these cyclic or circular corkscrew structures, or these pleated sheet forms, and then they'll form more of a tertiary or complex 3D structure at a given pH, at a given temperature and a salt concentration. It will take on this particular form shape. Quaternary structures, where we have 2 or more of these proteins that interact together to make a full complement of whatever the protein structure is. So just to review, the primary structure is the amino acid sequence, and so of a particular protein. And then we have the secondary structure, which hydrogen bonding between the amino acids. We start to form these twists and corkscrew-like shapes, and then zigzagging folding of these pleated sheets, as we see here. And that is the secondary. And then the tertiary structure is the complex three-dimensional shape formed by folding and bending of the secondary structure due to bonds such as hydrogen bonds or covalent sulfur to sulfur bonds. Help make this tertiary structure, and a lot of times this is the active form for many of the proteins that we have. In the quaternary structure, where we have two or more polypeptide chains held together between the amino acids in the different chains. Hemoglobin is a good example, where iron is held in the center, responsible for oxygen and CO2 transport depending on where it is. So the quaternary structure is two or more polypeptide chains bound together, forming this complex form of proteins that do various things. So just to try to put this in some terms that might help, egg whites contain much protein, so we can heat the eggs, and if you notice, we can denature the egg protein by as evidence of them turning white as we cook them. So why does beating eggs change their texture, making them stiff? Well, you're randomly breaking up the various proteins and taking them out of their natural shape and structure and disrupting them by this process. Normal protein has its normal shape according to the way that protein was to be designed, if I can use that way. Extreme environment, heat, pH, disrupts the protein shape and function, so we can denature it. So beating the egg will change its structure, and more randomness, and tends to thicken them up. So why is wet hair easier to style than dry hair? Well, when we apply water, of course, it covers the structures with the water, and will tend to make them lay down structurally or chemically not as interactive, as because water is dissolving some of those bonds. So why do some people have curly hair and others have straight hair is the way the proteins were laid down, and perhaps having more sulfur to sulfur bonds, creating some kinkiness for the bending or the changing of the hair. So it's genetic from a large point of view. We'll talk about that. The particular amino acid sequence of a protein determines how it folds into an important particular shape. This shape determines many of the protein's features and function, such as molecules that it interact with. So structure and function is one of my, of course, hot buttons there. When a protein shape is deformed, the protein usually loses its ability to function. So if we disrupt its quaternary or tertiary structure, it no longer will function the way it was intended, or the way it evolved. Enzymes are proteins that initiate and speed up chemical reactions, but they're not consumed in those reactions. So enzymes facilitate chemical reactions. Enzymes can help bring about chemical reaction in a variety of ways. Enzyme lactase, for example, breaks down milk sugar lactose into two simple sugars that can be used for energy. So using lactase, and now a lot of enzymes will use the ASE ending, and that indicates that it is an enzyme, and lactase will break or put pressure on the bond between the two, greatly reducing the energy it takes to break that bond at the molecular level. So at the enzyme is now service. We have 100 trillion cells in our body, and what we find is that the enzymes help reduce the budget required to maintain life. So to make ends meet, enzymes can be reused over and over again, and what it's doing is it reduces the amount of energy it takes to catalyze various reactions. The structure of the enzymes, as we mentioned before, its tertiary or quaternary structure, is such a way that there's charge and folding that facilitate now this interaction. In this particular case, at the molecular level, the lactose will fit right in, sort of like a lock and key. So we have the substrate, which is the lactose, and they fit in the enzyme itself like a hand in glove. And you can see this like a key in a lock. Lactose fits the active site in the lactase enzyme. The bond between the simple sugars are stressed on and then are broken, and then the two sugars are free to leave, and then the enzyme can be reused. A very efficient system, very clever. Incorrect amino acid sequences can have a deleterious effect, a kinking of a protein, and disrupt its overall structure. Active sites are disrupted. Phenylketonuria is an example. Having ketones in your urine, so keto and urea, this is urine, keto is ketones or proteins, especially the phenoproteins, phenylalanine. And what happens is an enzyme that breaks down phenylalanine no longer functions properly, so we get a buildup of phenylalanine. And too much of anything is bad, but in the case of phenylalanine, it can be toxic. So if we break down an enzyme, or an enzyme's damaged that breaks down phenylalanine, then you'll get a buildup of that. So patients for PKU or phenylketonuria patients have to stay away from phenylalanine in their products. So some artificial sweeteners contain a lot of phenylalanine, and you'll see that PKU patients need to be aware. Lactose intolerance, even a slight alteration in the enzyme's active site can disrupt its functioning if the enzyme lactase is not built just right, and an individual cannot digest milk properly. This is lactose intolerant, or we can have a hormone bind this site that prevents this, and you have lactose intolerance. Sometimes women, after giving birth to children, will have lactose intolerance for a while, for a period of time, and that's because hormones will block that site, but it's usually temporary. Enzymes are proteins that initiate and speed up chemical reactions. They aren't permanently altered in the process, but rather can be used again and again, which is a very important aspect of protein building. Nucleic acids store the information. This is where the recipes are kept, how to build and run. And it's sort of, if you look at it from a software analogy, it is the code at which the hardware implements and executes the code. That's very similar. So we have 4 bases: adenine, thymine, guanine, and cytosine. Adenine and guanine, if you look at the structures, are purines, and thymine and cytosine, looking at very similar structures, are pyrimidines. And so we have these 4 bases that encode all of life, and these codes that build proteins eventually through the process of DNA to RNA to a protein, the central dogma theory, is a resulting of the arrangement. So it's 4 keys on the piano creating the concert of life that we see today. It's quite amazing. So the backbone is a phosphate backbone. We had Watson and Crick had identified a 2 backbone structure of DNA, elucidated the structure, and now we have the Human Genome Project, where we've sequenced all of humans, I don't know, probably over 600 different individuals now, animals, plants, all sorts of things that we've sequenced, and know the arrangements of these 4 bases. It's quite amazing. So we have DNA, which is deoxyribonucleic acid, and RNA, which is ribonucleic acid. So one of them have this deoxy take a particular structure out, where RNA has that particular structure, and I'll look at that with you. But we have the phosphate backbone, the sugar structure, and then the base. And we'll talk more about the differences. There's really simple and subtle differences between DNA and RNA. RNA is usually single-stranded, although it can bind or fold and cause double-strandedness in some regions, but not to worry about that right at the moment. Information storage is the key. The information in a molecule of DNA is determined by its sequence of the bases, adenine, guanine, cytosine, and thymine, and however the sequences are. We use a single letter in most cases to designate this. So we have cytosine, guanine, adenine, thymine, thymine, adenine, cytosine, 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 guanine, adenine, and thymine in the sequence given here on the screen. One of the differences between DNA and RNA is that one of the bases are substituted for uracil, and that's really important, and we'll come back to that here in a minute. So nucleic acids, DNA and RNA, are macromolecules that store information, genetic information, by having unique sequences of these molecules. Both play a central role in directing protein production in organisms. Of course it does. So DNA holds the genetic information to build an organism, and that we can see certain prediction of bindings between these purines and pyrimidines. In this case, adenine and thymine have 2 hydrogen bonds, where guanine and cytosine have 3. So adenine always pairs with thymine, and guanine always pairs with cytosine. And you can see the 2 sugar backbone phosphate bonds there. So A's and T's, adenine and thymine, and guanine and cytosine, a purine and a pyrimidine always bond together. What is the complementary strand to this? So we have CCCC, so we would have what? GGGG. In 2 T's, we'd have 2 A's. We'd have now an A, we'd have a T. We have 2 G's, we'd have 2 C's. 2 A's, we'd have 2 T's for the complementary, and of course, if we had 2 C's, we'd have 2 G's. So that would be the complementary strand of GGGG, AAT, CC, TT, GG, and that would be the correct complementary strand. DNA is also like a ladder, which the long vertical element of the ladder is made from a sequence of sugar phosphate, the sugar phosphate molecules. Rungs are the nucleotide bases held together by this hydrogen bonding. The sequence of the nucleotide bases contain this information about how to produce a particular protein. And so that is the key to life in terms of being able to reproduce and to accurately generate that organism. RNA is universal translator, reading DNA and directing protein production. So we go DNA to RNA to a protein. That's the central dogma. So the RNA structure, there's 3 important differences between RNA and DNA. The sugar molecule in the backbone contains an extra oxygen, hence DNA being deoxy. RNA does not say deoxy, it just says ribonucleic acid, so there's 1. RNA only has 1 sugar phosphate backbone, so it's single-stranded, not double-stranded. Instead of thymine, RNA has a base we call uracil, and it's just really just a methyl or CH3 group change, but nevertheless uracil is different, and that is associated with RNA instead of thymine, so please keep that in mind. RNA acts as a middleman molecule. It takes because it's single-stranded, it breaks down. If you ever watched Mission Impossible, good evening, and this tape will self-destruct, and that's sort of what RNA does. Once it's encoded, it builds some proteins, and then it is broken down rather within, let's say, 10-15 hours or so, and that way we don't have RNA just sticking around everywhere and all sorts of proteins being made willy-nilly. They're expressed and made, which is a temporal thing. So they are the recipe or the template for making a protein, and that's what makes life possible. RNA differs from DNA in 3 important ways. The sugar molecule of the sugar phosphate backbone is not a deoxy, contains that extra oxygen. Single-stranded, in other words, it doesn't have 2 backbones, only has 1, and then uracil replaces thymine. If you can remember those differences, that would be wonderful. RNA acts as a middleman molecule, taking instructions for protein production from DNA to another part of the cell, where, in accordance to the RNA instructions, amino acids are pieced together into proteins. And that is the important aspect. So, understanding our learning objectives: describe what atoms are, their structure, and how they bond. Understand water's features, the surface tension and the the thermal aspects and the bipolar nature of water molecule itself, describe carbohydrates or structures, be able to describe lipids, proteins, and nucleic acids, all of which relate their structure and function. If you can do that, then you'll do well in chapter 2. I have study guides online, various different forms. I have the visual learning guide. I have the sort of a worksheet, which is study guide, and then my study guide, which is just an outline, sort of a inventory of things to make sure that you know. And then I have roots of vocabulary at the end there to help you in your determination of what these words mean. Vocabulary is very important to study in biology, so don't take that one lightly, because really understanding the language will help you in your quest for getting things done. So thank you for your time, and I'll see you in class, and I look forward to going on to chapter 3 at the appropriate time. If you have any questions about this presentation, please bring your questions to class and we'll go over that. Thank you.